Following our discussion on finite op-amp gain, let's now tackle another crucial non-ideality, op-amp nonlinearity. Ideally, an op-amp provides a perfectly linear relationship between its input and output. This means its output voltage is simply its input voltage multiplied by a very large, constant gain. If you were to plot this, it would be a perfect straight line. However, in reality, this relationship isn't perfectly straight. It has some curvature. This deviation from linearity is a source of error in our ADC. To understand and analyze this error, we need a mathematical model. This page introduces a common way to model this behavior when the nonlinearity is relatively small or weakly nonlinear. We can approximate the op-amp's open-loop characteristic with a third-order polynomial, as you see in the first equation. It states that the output voltage V underscore is a function of the input V underscore n. The first term, alpha V underscore n, represents the ideal, dominant linear gain that we want. The alpha coefficient is essentially the main gain of the op-amp. The terms that follow, alpha 2 V underscore superscript 2 and alpha 3 V underscore superscript 3, are the error terms. They model the curvature or the nonlinearity. These terms are responsible for creating harmonic distortion. What does that mean? Well, if you put a perfect sine wave into this nonlinear op-amp, the alpha 2 term will create an unwanted signal at twice the frequency of your input sine wave, the second harmonic, and the alpha 3 term will create another unwanted signal at 3 times the frequency, the third harmonic. These distortions corrupt the signal we are trying to process. Now, when we analyze a circuit like our ADC which uses feedback, it's often more convenient to express the op-amp's input voltage in terms of its output voltage. That's the purpose of the second equation on the slide. It gives us the inverse relationship, V underscore as a polynomial of V underscore. This inverse polynomial has its own set of coefficients, beta 1, beta 2, and beta 3. As you can see, these beta coefficients are directly derived from the original alpha coefficients of the forward model. You don't need to memorize these specific conversion formulas, but it's important to understand that they provide a direct mathematical link between the forward and inverse models of the op-amp's nonlinearity. So, this page has equipped us with the mathematical framework to describe this particular imperfection. On the next page, we'll see how we can plug this nonlinear model into the equations for our ADC to figure out how it affects the residue voltage and the overall performance of the ADC. Continuing our exploration of op-amp errors, this page shows us the practical effect of the nonlinearity we just modeled. Previously, we described the op-amp's behavior with a polynomial equation. Now, we see what happens when that non-ideal op-amp is actually used in a pipeline stage. Take a look at the graph of the residue voltage V underscore S versus the input voltage V underscore N. For an ideal 2-bit stage, this should be a perfectly linear sawtooth waveform with sharp peaks and valleys. However, the purple ovals highlight a significant problem. The peaks of the waveform are compressed, or they droop down, and the valleys are pushed up. The transfer function is no longer a straight line. It's curved near the reference voltage limits. This distortion is the direct result of the op-amp's gain changing with the output voltage level, which is what nonlinearity is all about. So, what is the consequence of this droop? The key issue is that the residue voltage V underscores never reaches its full intended range. Because the peaks are lower and the valleys are higher than they should be, the input range for the next stage in the pipeline is reduced. When the next stage tries to digitize this compressed residue signal, it finds that certain input voltages and therefore certain digital codes are simply unreachable. This is what we call missing codes. Imagine you have a digital scale that can show 10 grams and 12 grams, but it can never, ever display 11 grams. That's a missing code. It's a critical error that directly impacts the ADC's accuracy and linearity. The complex nonlinear equation at the bottom provides the mathematical foundation for this effect. It's essentially the charge conservation equation for the MDAC circuit, but it's been updated to include the non-ideal op-amp model from the previous slide. The left side represents the charge sampled on the input capacitors. The right side shows how that charge is redistributed, but instead of a simple ideal relationship, it incorporates that polynomial expression with beta 1, beta 2, and so on, to account for the op-amp's nonlinear behavior. By solving this equation, we can precisely calculate the distorted residue characteristic we see in the plot. The main takeaway is that this nonlinearity directly leads to the compression of the residue signal, which in turn causes those harmful missing codes in the final output.